What's up, brother? Mr. Robinson back here with yet another brand new exciting video, all math-based, of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, we are doing our Chapter 10 review in the Big Ideas Math Integrated Math 2 textbook. This is on circles. I've already mentioned several times before that if you jump into Chapter 11, there are other things involving circles. Not everything here was hit. But the relationship with like lines and circles and 10.7 hit some things with graphs. And this review will cover them all. So if you check out the PDF down below, you can download this thing. Check the description section as well for timestamps for each part. I think it's numbers 1 through 46. There are actually a lot of problems. Makes me feel like we'll be able to drill and kill through a lot of them, but they also lead in with some problems before with each section. So we get to explain the section a little bit before, or at least as much as the book kind of tells us what to do. So I'm just going to jump into it, guys. We'll go straight ahead and take a look at what we have. Starting with this 10.1, lines and segments that intersect circles. And honestly, in some ways, I'm almost forgetting of what's going to be what. I remember in this section, they have you identify things by name. They're doing that here in this first step. But before that, let's look at a mathematical connection they have from an example problem. In the diagram, segment AB is tangent to circle C at point B, and segment AD is tangent to circle C at point D. Find the value of x. So in this set, when you have two tangent lines connecting to an external point right here, those two tangent lines are congruent to each other. There are proofs to that stuff, and I think we did it at the time, but basically you set this equal to that, which is what they do. You subtract 5, divide by 2, you get x equals 14, and that will be your answer. So there is the one example. Let's go ahead and take a look at these numbers 1 through 6. This whole section goes, I think, all of 1 through 12. This is why there's so many questions. The first 6 are part of the same diagram. Tell whether the line, ray, or segment is best described as a radius, chord, diameter, secant, or tangent of that circle P. And it's called circle P because this, like circle C on the previous problem, because it's the center. P is the center on this one. C is the center of that one. From P to K, P being the center to K, that is a radius. So PK is a radius. Radius is the distance or a segment drawn from the center to your circle itself. Segment NM, I gotta bring this thing over. Sorry about that. Number 2, segment NM. I don't know where they are yet. I'm just writing this down and trying to fix this. Okay, segment NM is it's a chord. It shows segment, and it's going from N to M. A chord is any segment that is from both endpoints around the circle itself. Did they give the... Okay, so I didn't know they had that option there. Number 3, JL, and JL is a ray, so not a segment. So ray, JL, where is that? From J to L, touching K along the way, K is a point of tangency, so this ray would be considered a tangent ray, if you will, but I'll just state a tangent, as it only touches it at one point, like that. Number 4, we have segment KN. KN, you could describe as a chord, but they ask you to best describe it. KN is the longest chord in the circle because it goes through the center. Segment KN is known as a diameter. Probably a word you knew well before chord or tangent. Radius and diameter are probably ones that you're like, yeah, I got those ones. Number 5, line NL. From N through point L and also hitting point M, this could not be described as a chord because it doesn't have endpoints. It's a line, it goes on forever, and it touches the circle twice. This is known as a secant. A secant line in this case, but a secant. And lastly, number 6. Is there one we haven't said yet? Segment PN. PN's another diameter. PN's another diameter. Another radius. Another radius. It is two opposite radii, or two radii that fall on the same line make a diameter. Diameter's twice a radius. See, we're not doing that kind of stuff really as much here. We're not doing like circumference and diameter and things like that. There are infinite number of radii and there are infinite number of all these things in a circle, so don't just assume the ones are drawn. From P to M would have been another radius, for example, if they had that. They didn't. Okay, now we didn't really do anything with these parts here after, and I don't really have any plans to do anything with them, but it's to help you understand what tangency means as a whole. Tell whether the common tangent is internal or external. Now, I'm not going to redo the drawings, so I'm just going to kind of keep them as they are. It's an internal tangent if you can draw a segment from one center to the other in a circle and your line crosses through there. It is a tangent line since it hits each circle once, and this is an internal tangent since it's going in between the circles in the way that you could draw a segment between those circles and it hits. So number 7, I'm just going to write internal. Hope that's okay. Because they're not having me draw them, so I'm just going to go straight off that. Number 8, this time, again, drawing a segment from one circle to the other. It stays outside of them like that. That does make this one an external tangent, and I'll just go ahead and name it as such. So number 8 is an external tangent. Now we get to numbers 9 through 11, where they state that points y and z are points of tangency on every one of these problems. Point of tangency, and no point y here, but z is a point of tangency on there. Find the value of the variable. The first two, numbers 9 and 10, will be just like the example one that we saw. You set these two parts equal to each other because these segments are congruent. This is congruent to that, so I can set 9a squared minus 30 equal to 3a. Now this problem isn't as easy as the one that they had set up because this is a quadratic. So we have to solve this quadratic. I'm going to subtract 3a to this side and write this thing in standard form in hopes or in anticipation that it's factorable. And if not, we'll use the quadratic formula. I'd love to divide everything by 3 first, make it smaller for myself. I hope that you choose to do the same. This is factorable. I'm just trying to determine. I know where to go with this. I'm going to use 5 and 2. If I multiply this one by the 2 and this one by the 5, let's see, I said that wrong. This one by the 2 and this one by the 5, -6 there plus 5. So 5 times -2 is -10, 3a times a is 3a squared, and this is -6a plus 5a, which is -a. That's the factorization. You could use quadratic formula. If you have zero product property there, again, this is more first semester stuff with algebra. Either this equals 0 or this equals 0. If a minus 2 equals 0, then a equals 2. And if 3a plus 5 equals 0, 3a would be -5. And then a would be -5/3. Now, you need to look. I feel like I gotta sneeze again. It seems like I must be allergic to stuff in my room. I must have like dust stuff building up because I never sneeze. I gotta sneeze. Hold on a second. Okay, anyway, I was stating that I'm not sneezing until I get in my room, so I need an air purifier or something like that. Do both answers work? When I plug in 2, I have I'm going to get the same value, but do both answers work? When I plug in 2, I get positive numbers out for both. When I plug in -5/3, I actually do get a positive number for this first one. But I get a negative for, well, actually, no, I don't. Actually, I take it back. They'll both be negative. When I square this, it starts positive, but -30 must turn negative, and this part turns negative. So the -5/3 actually doesn't work. It's just a equals 2 that actually applies to this one. All right, let's jump to number 10 with that in mind. It looks like another quadratic, but possibly an easier one for reasons I'll state when we get into it. So number 10, we get to set these two equal to each other again. We get 2c squared plus 9c plus 6 equals 9c plus 14. Excuse me, we subtract 9c from both sides, and you're going to see that they're actually going to cancel out. So I'd rather isolate my squared quadratic term, quadratic term, and I'd subtract 6 over to this side to solve this, because I can solve using square roots. Divide both sides by 2, and take the square root of both sides. Now, in this case, you would generally get c equals plus or minus 2, but 2 is the only one that can apply. -2, once again, would give you a negative value, a negative length. You must have a positive length. It cannot be negative or 0. Let me address more sniffles. Okay. We finished 10, right? Let's move on to number 11. Now, number 11 does not have 2 tangent segments. It only has 1 from x to z. But x to z is a tangent segment, and w to z is a radius. Now, there is a theorem that states when a radius intersects at the point of tangency with another segment, that it makes a right angle here. So we actually have a right triangle in this WZX, or whichever way you want to say it. It's a right triangle. So they want you to solve for r in this case, and in right triangle form, we can solve using Pythagorean theorem. So we can do an a squared plus b squared equals c squared setup. Not that any two things are equal outside of this, but r squared plus 9 squared, those are the legs that make the right angle, equals, and then you have r plus 3 quantities squared as what would be the hypotenuse. So we're going to try and solve for r with all this in mind. This won't end up staying quadratic, but we do need to expand this out, and this becomes r squared plus double 3r, so 6r, plus 3 squared, which is 9. But the r squareds will cancel. They are gone. So you're left with 6r. You know, we got to solve for r from that. I'll subtract 9 from both sides and get 72. Divide both sides by 6. You get r equals 12. And it looks like 12 should pan out just fine. There's no plus or minus 12, anything like that. That's the only answer from there. Number 11. Number 12, tell whether a segment AB is tangent to C and explain. This is, if it was tangent, then this diameter, which contains radius, by the way, would make a right angle with this. So in order to make a right angle with this, this would have to be a right triangle. And in order to be a right triangle, then a squared plus b squared would have to equal c squared. So we're going to test that theory. These would ideally be the legs, and this would be the hypotenuse. Now, this leg is not 10. It's actually 20, because 10 is that radius. This is one of those setups where you'd have to know that a diameter is twice the length of the radius. So we got to check, and I don't know. Is 20 squared plus 48 squared equal to 52 squared? I think it's going to be. I believe that this is part of the 5, 12, 13 Pythagorean triple ratio relationship. Like, I almost want to divide everything by 4 to state that. But this would be 400. I do not know 48 squared. Hold on. 48 times 48. 2304. 2304. And does it equal? I think it's going to. Does it equal 52 squared? 2704. Yes. That would be 2704 equals 2704. Therefore, it's a right triangle. Therefore, that's a right angle. Therefore, segment AB is indeed tangent to C. Only at a right angle does that happen. So that's a converse, you know, a biconditional theorem. Its original theorem is true, its converse is true, and that's what we tested there. That's probably the end of 10.1. It is indeed. Let's move on to section 10.2, finding arc measures. So before we start this number 13, let's look at some of the 3 examples we have above. Find the measure of each arc where Ln is a diameter. If Ln's a diameter, well, let's talk shortly on a couple things. Number 1, we're talking about central angles, like this guy, or this guy, or this guy, or this guy. Any central angles have the same measure as their intercepted arc. So if this is 100 degrees, then this is also 100 degrees, things like that. We also name arcs based on a number of letters. We use 2 letters for minor arcs. If I want to say from this K to L, I would call it arc KL. But if I want to go from K to L the other way, called a major arc, more than 180 degrees, I got to use like KNL or KML to do that. I need 3 letters to do that. They mentioned this diameter for this example. Ln's a diameter, which is important to state. It's a straight angle of 180 degrees. This makes a semicircle, which means that's 180 degrees as well. So we're going to use some of that information to answer some of these. They need the measure of arc MN. This will be 120 degrees because its central angle is 120. So that's what they show there. The arc NLM. So NLM needs to go to L before it hits M. What I would probably do here is find out the measure of arc LM by using the 120. And 180 minus 120 would give us 60 here. Oh, I guess they did something else. But, oh, we still need to find this one as well. Oh, okay. Well, let's see what else they said. 360 minus 1. Oh, I'm sorry. Yeah. They have the whole thing. Okay, that's better off that they did that. So, remember, this one's 120. That's the minor arc. So, the major arc is everything that's not the 120. So, they did 360 minus 120 and got 240. Duh. I was looking at, I thought it was just these 2. And then the third one, NML. NML, that is a semicircle. It's a semicircle, so that'll automatically be 180 degrees. Boom. Nothing really to calculate. Those are the example ones. Let's go ahead and look at the ones that they have for us. Let's start with number 13. Use the diagram above. Oh, there, we're still using the same diagram. So let me copy and paste that. Give me 1 second. In case I want to just like do more. Use the diagram to find the measure of the indicated arc. This was the first one I actually stated. I wasn't aware. Arc KL. There's the minor arc. That will be 100 degrees. Did they state any other ones that I could write in right here? I don't think so. We just did kind of bigger arcs. So let's keep moving on. Number 14, measure of arc LM. This one I will write in after we figure out what it is, and this is one I was talking about before. LM is this minor arc here, and it's part of this semicircle. The semicircle is 180. Let's take away the 120 that's here. This is 100 and 120. Semicircle is 180, and then minus 120 is 60 degrees. So measure of arc LM is 60 degrees. So I'll write it, right? We can possibly use that in the future. Number 15, measure of arc KM. KM? Yes, KM. Now, we need to do the minor arc. So from K to M, we're going to go this way, the path that'll take you less than 180 degrees. We have a 100, we have that 60, which we can use, so we add those two. We're using something called the arc addition postulate. You can basically add arc measures together, and it becomes a thing like that. So again, that should be less than 180, given that it was 2 letters. They are referencing a minor arc. And then number 16, measure of arc KN. It's the last one that we haven't yet figured out. You could add all of these up and subtract from 360, but better yet, I suppose, this is another semicircle on this side with LKN. So let's take away 100 from 180. I think that's just the faster approach. So measure of arc KN is 180 minus 100, so 80 degrees. Okay, that's 13 through 16. Let's have new diagrams. 17. Tell whether the red arcs are congruent. Explain why or why not. So if you notice here on number 17, you have a red arc inside ST and a red arc outside YZ. Now, they would happen to have the same measure, and the reason they'd have the same measure is because these two central angles would be congruent to each other, given that they're vertical angles, and central angles have the same measure as any of their intercepted arcs, the WX or the YZ. They have the same measure. Therefore, these also have the same measure, so as far as measures go, they're equal. If this was 60 degrees, so is this. If this is 60 degrees, so is that. Does that make them congruent? Not quite, because these circles are not congruent. There's one circle that's bigger than the other. Same measure does not mean that you can lay the other one right on top. They lay one right on top of the other. They are not equal in size and shape. So let me type the one out. Not congruent, that's the ST and YZ. Although they are the same measure, they are of non-congruent circles. Therefore, they're not congruent. Okay, so therefore they're not congruent. That apparently is not a word, so there we go. Okay, so that's number 17. Let's look at number 18. Interesting drawing. Let's see if I can explain out what it is I'm looking at. So on number 18, well, I have enough of what I can see here. If you can tell, you have a circle, C, that has a radius of 6. You have another circle, D, that has a radius of 6. That makes these circles congruent. Then you have 95-degree central angles here and here, which are also same measure and congruent. Their intercepted arcs should also be the same measure, and because the circles are congruent, then those arcs will be congruent. So in this case, yes, congruent. They are intercepted arcs of congruent central angles from congruent circles, verified by their radii. So they have a radius of 6 each, therefore the circles are congruent, and yada, yada, yada. All right, let's keep going forward. I'm averaging about a minute a problem with examples. Let's go to section 10.3 on using chords. I forget which section is what as we move forward, so I'm just reading out loud. We're going to do the chapter 10 test. I'll do a video of that shortly after, and that's not going to tell you what section something's from. So in a vacuum, I suppose these are pretty easy, but when they throw anything at you, you still got to know what to do. In the diagram, circle A is congruent to circle B, so they're telling you that. Their markings indicate this as well. And segment CD is congruent to segment FE, and measure of arc FE is 75 degrees. Find the measure of arc CD. So I'm going to read what they say and see if there's anything else I can say. Because CD and FE are congruent chords in congruent circles, the corresponding minor arcs CD and FE are congruent. Therefore, measure of arc CD equals measure of arc FE is 75 degrees. So they said it all. If you're within the same circle with congruent chords, those minor arcs would also be congruent to each other. So if I had another one right here that's like that, these would also be congruent. But because the circles are congruent, that also works. One 75, the other 75. That doesn't mean each question will be like that. But if we run into ones like that, then we'll be good. Start with number 19. Find the measure of arc AB. Okay, so I think we already start there. And here's kind of the reason why this does work, because this chord has these endpoints that the central angle also has of this degree. So if that's 61 degrees, then so is this. Now they show this chord as well with the same bits. That means that it has the same reach for this central angle to also be 61 degrees. That means that's 61 degrees as well. So same circle, congruent chords. They're not asking us to explain why, but that's it. Therefore, measure of arc AB is 61 degrees. It's probably one of those things where even if you weren't taught that, you could almost just assume it. You're like, yeah, it looks like it. Number 20, the measure of arc AB here. Now, this is a different scenario completely. What we do have is two chords that are perpendicular bisectors of each other. There's a converse of a theorem that states that the original theorem states if a diameter is perpendicular to a chord, then it bisects that chord and it bisects the arc right here. And there are reasons for it that you can prove. This one is the converse of the theorem. If two chords are perpendicular bisectors of each other, then the one that's if one chord is perpendicularly bisecting the other chord, then that original chord is the diameter of the circle. All this to say that that diameter is also bisecting this arc. So that arc is divided into two congruent parts. If this one's 65 degrees here, this is also 65 degrees here. That's what they're asking for, the measure of arc AB. So measure of arc AB is 65 degrees. Number 21, this is a different theorem where you have two chords that are equidistant from this center. We know they're equidistant because they show the congruent marks. They show the perpendicular part, which means shortest distance is the same. When they are both equidistant from there, then the chords are congruent. And if you have congruent chords, then you have congruent minor arcs stem from these. So if measure of arc ED is 91 degrees, then measure of arc AB is also 91 degrees. Once again, one of those things that you could probably just look at and go, is it 91? Yeah. But hopefully you can kind of get the where and why of that. Okay, number 22. In the diagram, the length of segment QN is equal to the length of segment QP. So once again, equidistant from the center are these chords. Therefore, the chords will be congruent. They don't tell you that, but that's what that means. JK is 4x. So that's the length of the segment. That is not the arc. That is the segment. And LM is 6x minus 24. Find the radius of circle Q. So there's a lot we can do here. Probably enough that I'd like to copy and paste this thing over. So we just got off of a previous problem where we mentioned that two chords that are equidistant from the center are congruent to each other. So the very first thing I'm going to do is, without figuring out what else I want to say, is solve for x. Solve for x, where 6x minus 24 equals 4x because these two things should equal each other. Let me state kind of one more thing on that. JK should be equal to ML because those segments should be congruent. So we set those equal to each other. We solve for x. I subtract 4x from both sides, add 24 to both sides, and divide both sides by 2. Now, this is not the answer. We need to find the radius of the circle. Now, the radius can appear in multiple formats. Here's an example of the radius. Here's an example of the radius. Now, you don't have to go by what they use. What you actually tend to want to use is one of purpose, one that's going to be helping you. One that would help me is some sort of radius that goes, say, right here, from Q to M. Because what I can now form is a right triangle. And in a right triangle, I can use Pythagorean theorem to find this radius. In order to do that, what did solving for x have to do with this? In order to do that, I need to find this length here and this length here. Now, I don't actually know how to find that length, so I'm trying to think of how I want to do the radius with that in mind. That is a good question. Those are congruent, but that's not all the information. Now I'm actually at pause thinking about what I want to do with that. I do know how to find this length of MP. Let's start with that and see if I can figure anything out in the process. They must have told us a length. Oh, QN and QP are 10. There we go. I was going to say, I'm going to have to pause this video. This seems impossible. So QP is 10. MP. How do I find MP? Start with ML. ML, based on X, is 6 times 12 minus 24, which is 72 minus 24, or 48. MP should be half of it. Why should it be half of it? Because when a radius or diameter is perpendicular to another chord, then it bisects the chord. So if ML is 48, then MP is half of 48, which is 24. So we have a length of 24 there. I should probably put 2 congruent tick marks. So we now have a right triangle with a length of 10 and a length of 24 as the legs. And the hypotenuse is the radius, which we need to find. I'll call that R. This is where we finish this thing off, where 10 squared plus 24 squared equals R squared. And this isn't the first and last time, or maybe it's the last time. It's not the first time that we've seen a 5, 12, 13 Pythagorean triple. This is double, double, and double 13 should be 26. Let's go ahead and do the rest of the work. 100 plus 576 equals r squared. R squared equals 676. I think it's fair to assume that r is going to equal 26 from what I stated. I have no idea if that's the square root. Sounds right. I'm going to go with it. And that's the radius of the circle. So a lot of properties came into play, but I'll be honest, there have been a lot of problems like this that we've also seen if you've been with me on this journey on section 10.3 and the review and stuff like that. That's it for 10.3. Let's go and move on to 10.4. I probably lost pace, and that's okay. We're up to 46 problems, so we're almost halfway through. Find the value of each variable. So we have a quadrilateral inscribed in a circle. They want to solve for A and B. In an inscribed quadrilateral, that there is a truth that opposite angles are supplementary to each other. That's what they're saying here. So this angle M plus angle P is 180. This angle L plus angle N is 180. And because they have separate parts of variables, we can use that to solve for these. So they did 3A plus 3A is 180. They solve for A, they get 30. And they do B plus 50 is 180. Solve for B, and they get 130, excuse me. And that's the example. Is that everything that's done for out of section 10.4? Heck no. In fact, that's probably very little with what we talk about. The whole inscribed angles thing that we want to talk about mostly is that an inscribed angle is measured as half the measure of its intercepted arc. If this angle, I'm going to start 23 right now. 23, if this angle is 40 degrees as an inscribed angle, unlike a central angle, it's not equal to its intercepted arc. It's half of the measure. So x is double that of 40 degrees, which is 80 degrees. When they ask you to find the value of the variables, that is x, that is number 23. Now number 24 goes back to our inscribed quadrilateral, so opposite angles are supplementary. Let's solve for both r and q. So I'm going to solve for q first. Q plus 80 is 180. Those are opposite angles. Subtract 80 from both sides. Q equals 100. I guess x doesn't need to have degrees in it because I was going to say this other one doesn't. R, we have 4r plus 100 equals 180. Another supplementary bit as they're opposite each other. Right there. Subtract 100 from both sides. We get 4r equals 80. Divide by 4. We get r equals 20. Let's go to number 25. This time we have inscribed angles. And this, part of the trickery is even if you know the formula and stuff, you have to recognize the figure for what it is. I have an inscribed angle right here with this intercepted arc. I have an inscribed angle right here with the same intercepted arc. Two inscribed angles that share the same intercepted arc must be congruent to each other. They must have the same equal measure. They both have to be half the measure of their intercepted arc. Now, this one kind of goes in a different way because I don't know the measure of the intercepted arc, but I could find it. If this is 70 degrees, that's half of what this arc is. That means this arc is 140. Therefore, that 14D must be half of the 140, which is 70. So 14D equals 70, right? They are congruent to each other. 14D equals 70. Instead of going that long way around it, we can go straight to here. Divide both sides by 14. You get D equals 5. Number 26. This one has and here's another piece. We have a diameter going through here, which is important to state because that means this is a semicircle. And a semicircle measures 180 degrees. If this is 180, then its inscribed angle with that intercepted arc is half of that. That means this is 90. That 3y equals 90 degrees. We'll start with that one, and then we'll find out what the other ones are. 3y is 90. So you divide by 3, and you get y equals 30. Now, I didn't need to plug in y back into there because I know it's 90, so I'm just going to go and make that a right angle right now. This is 50 degrees, and in this right triangle, the acute angles of that should be complementary. So I don't really need to use that 30 for this part here. Let's just go ahead and say that 50 plus 4z equals 90. The two acute angles in the right triangle add to 90. Subtract 50 and divide by 4. You get z equals 10. Okay, number 27. We got a couple of those inscribed angles again. Check out where their intercepted arcs are. Hopefully we can really narrow this down. I'll do M first alphabetically. So M is this inscribed angle with this intercepted arc. However, 44 is this inscribed angle with this intercepted arc. Since they share the same intercepted arc, they are equal measures. M is 44. N, same thing, inscribed angle, the intercepted arc RS, 39, inscribed angle with the intercepted arc RS, therefore N is 39. There's nothing to calculate on these ones. Okay, number 28. C is half that of 56, being an inscribed angle. That's one of the, not more basic problems, but that's one of the more conventional kinds of problems that you would see here. So C is half of 56, which is 28. Hey, that's the question number. Cool. All right. Section 10.5. Looks like I have no questions down here, but part of our preview. The book may talk about this a little separately than I do. I'm big on simplifying the formulas for what they are. I've really made mention. You'd want to check out my lecture video portion for this thing, but I'll make a really quick mention of it here. If you want to, again, hear more of it, check out the video. So check out this angle right here that I'm drawing in green. It's outside of the circle. It's not an inscribed angle. But what if I treated it like an inscribed angle? What if I moved it so it was on the circle like that? An inscribed angle. That doesn't change this being 60 degrees, right? That's still 60. And then this, notice how this arc that was 190 before from Q to T, notice how it's now smaller here. It's no longer 190. In fact, you should know how much it is. How much should it be now? It should be 120, right? It should be 120 because an inscribed angle is half its intercepted arc. So it just lost a certain amount of degrees. It lost, oh, I'm sorry, the Y isn't 60 degrees. The Y is Y. I was like, something was wrong there. So the Y is still Y. That hasn't changed. But anyway, I guess we don't know what that thing is anymore. We got to find Y, right? We have no idea. Anyway, let me rewind. This Y angle, this intercepted arc should be twice that amount, or this should be half of that. But we lost some of the 190 degrees. How much did we lose? We lost that amount of it, that 60. That 60 is lost right there. So the whole idea of this is I like to treat these like inscribed angles, but when you back this angle up, though this arc gains amount, it gains that 60, so we have to subtract the 60 out to compensate. So what do they do? Because this is not our example, it's theirs. You have a tangent and secant. To me, that doesn't matter so much as there's an angle on the outside and two arcs that are captured by the angle. We're going to take half the difference of this arc and this arc together, because when we take 60 away from 190, we get what the inscribed angle would have been and what its intercepted arc would have been, 130. 190 minus 60 is 130. Half of 130 is 65. That's Y's value. I know that explanation might not have been perfect for you that fast, especially since I called it 60 degrees to begin with. Sorry about that. But that's how I treat these things. They're like inscribed angles, half the measure of what their intercepted arc would have been when it's outside the circle. So number 29, no difference here. Now there's more than one way to do this kind of problem, and they talk about it in different ways, but I'm going to go a little more practical for this one, and I can make mention of something else after. X is going to be half of 250 minus this other arc right here. Now to find out this arc, remember, all your arc measure total is 360, so 360 minus 250 is 110. So that one's a 110. X is half of 250 minus 110. That's half of 140 degrees, which is 70 degrees. So X is 70. Now, another way that you could do this problem is once you know what this 110 is, you could also do 180 minus 110. I know that kind of sounds weird because you're like, where does the 180 come from? There are a couple things you could do to get to that proof and show it. Part of it is what we just talked about on 360 minus whatever. Another way you could talk about it is, notice in the center here, these would be tangents, or excuse me, these would be radii intersecting with the tangents at 90 degrees. And if these add to 90, then these add to 180. And if this is 110 degrees, then this is 110 degrees. X plus 110 is 180. Therefore, subtract 110. X is still 70. So I go for the more conventional route of what I mentioned. Number 30. This time the angle is inside the diagram, and whatever this X is, then this X also is right here. Case in point, they're the same thing. I don't need both. I just need one. If I backed this angle up, however, as an inscribed angle, backed up right here, boom, notice how this gained arc measure. It's not just 152 anymore. How much bigger is it? It's actually 60 degrees bigger. That 60 that's over there, if I move this over, notice how we just lost an amount? That's gained over here. So you have to add those two arcs together that are opposite each other and take half of it like you would an inscribed angle. X is half of what its intercepted arc would have been, 152 plus 60, which is half of 212 or 106. I know sometimes it sounds like I'm saying a lot of words. If you heard this stuff before and learned it, especially off of me, then that's fantastic. It should make more sense. You should be able to recall it. I'm trying to, it might sound like I'm complicating it. I'm actually trying to simplify it. I'm trying to tell you how it's always half of this thing, what's gained, what's lost, things like that. On number 31, 40 is the degree measure of the angle, and that will be half of the 96 minus x, the difference of the bigger arc minus the smaller arcs that are captured there. So if you multiply both sides by 2, then that 1/2 is gone, and 2 times 40 is 80. But the 1/2 is gone. You're left with 96 minus x here. Add x to both sides, subtract 80 from both sides, and you get x equals 16. It's number 31. Number 32, here's another kind of thing. It says line L is tangent to the circle. Find the measure of arc X, Y, Z, this guy here. Now, 120 is the measure of the angle. This technically also can be served as an inscribed angle because any angle here with that intercepted arc, any inscribed angle that has the I did this wrong. Any inscribed angle with this intercepted arc is also going to be 120 degrees. Here's an example. This, if I draw it straight enough, this would be 120 degrees. This would be 120 degrees. Once it hits to the tangent part right there, it maintains that 120 degrees even still. So the intercepted arc should be half, the angle should be half the measure of the intercepted arc. So the measure of the intercepted arc should be double that inscribed angle. And yes, I do call it an inscribed angle. The measure of, because both the endpoints are on there, measure of arc XYZ is double that of 120, which is 240. Okay, let's go to section 10.6. 2 more sections to go and 14 more questions. Let's move this down. Find the value of x. This time we're not talking about arc measures, and I don't think we're talking about it the rest of the time. Now we're talking about segment lengths. Give me one moment. Segment lengths. Within a circle, when two chords intersect, there's a very simple relationship here that this times this equals this times this, and they'll say it as much here. So in terms of solving for x, they're going to be doing x times 2 equals 6 times 3, or they wrote 3 times 6. That's 2x equals 18. Divide both sides by 2, you get x equals 9. That's but one example. Of course, they don't show all of them and all the relationships. So number 34 applies to that kind of question, but number 33 does not. On number 33, you have 2 secant lines, and I honestly couldn't care less about what kinds of lines they are. They could be a secant and a tangent. We know 2 tangents are equal to each other, but these aren't equal to each other. Doesn't mean there's not a relationship here, and there is one. It goes like this, and I'll say it simply as my version of the formula. The outside times the whole equals the outside times the whole. And this is true for all those ones that are intersecting outside. So if I'm going to do outside times whole, the whole is 4 plus 6, that's 10. Equals the outside of length, that JN segment is x times the whole. Now you have to add x with 3, and what do you get? You get x plus 3. So this ends up being a quadratic equation. You get 40 equals x squared plus 3x. And we've done quadratics a couple times now. I'm going to subtract 40 to this side, and we get 0. This is factorable into x plus 5 times x minus, x plus 8 times x minus 5. And when you solve, you get x equals negative 8 and positive 5. Now, negative 8 does not apply because that would give you a negative length outside here. 5 should be good, so we'll ditch the negative 8. We'll keep the 5. We're all good. Now, we proved these ones back in this section, so I'm not going to sit around and prove these. It has to do with similar triangles and proportionality. Number 34 is one of those parts where it's not outside times whole or anything like that, just this times this equals that times that. We've got a lot of x's involved. I'm curious to see where it goes. So if I multiply x with x plus 3, that should be equal to the 2x times the 6 minus x. So it's the parts of the segment, parts of the chord that are segmented that multiply together, and then the other two multiply together. If I distribute Do not divide x's out, please. You may cancel a solution. If I distribute, I get x squared plus 3x equals, and distribute here, I get 12x minus 2x squared. So if I add 2x squared over, I get 3x squared. Subtract 12x over, I get negative 9x equals 0. This one has a common factor, not just of 3, but also x, which is very great for my zero product property, a little bit easier to work off of. So either 3x equals 0, therefore x equals 0, or x minus 3 equals 0, therefore x equals 3. But can x equal 0? It could actually, in this sense, 0 plus 3 is 3, 6 minus 0 is 6. Those are good, but this would be 0, and this would be 0, and you can't have 0 length. So 0 does not work in this case. You have to check on the 3 still. Positive, 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 and 6 minus 3 is still positive. So that one does work out. That'll be the 1 answer to this. Number 35 is like 33 to me. Even if the book wants to treat it differently because it has a tangent line thing, it does not change the outside times whole equals outside times whole nature that I did before. Now, this bottom secant line, the outside is 8. The whole would be 8 plus x. So outside times whole equals, now on this one, this tangent line, xw is the outside and it's the whole. So 12 times 12 is what I'm going to do, 12 squared. It still works. It's still what you do there. So I can distribute, I get 64 plus 8x equals 144. And subtract 64, I get 80, and divide by 8, I get x equals 10. Notice none of these, by the way, not that I put degrees for some of the other variables we solved for, these are lengths. So if they say inches and stuff, we'll put inches, but these are lengths, these are not arc measures that we're doing here. Now, we did arc measures, right? This angle is half of this minus this, and this angle is half of this plus this. So you still have to know all of those. I'm sure they could land them all in a single problem if they wanted to, but they're not. Different sections. Number 36, word problem. A local park has a circular ice skating rink. You're standing at point A, about 12 feet from the edge of the rink. Boom. The distance from you to a point of tangency on the rink is about 20 feet. Estimate the radius of the rink. I doubt anyone does this mathematically. When they're at a skating rink. Scientists probably do this stuff to figure out certain things that they want to do, and I meant engineers. Okay, this is an outside times whole equals outside times whole thing. So I got 12 as the outside from that AD segment. And then the whole would be adding 12 with those two R's, literally 12 plus 2R. Equals, and then 20 times 20. That's both the outside, that's the whole, that is 20 squared. If I distribute, I get 144 plus 24R equals 40. There's not much that's going to be different on this. The one thing is our units, we will have units. We will have feet for this one. Subtract 144, I get 24R equals 256. Divide by 24, you get R equals, I don't know. Is that 10 and 2/3? What? 256 divided by 24. Yeah, 10 and 2/3. They said estimate the radius of the rink. I'll go to the nearest tenth, so around 10.7 feet. It's 10.6 repeating. 10 and 2/3 feet would be an exact version if you want to say that, or 32/3 of a foot. Okay, last section we have 10.7 and quite a bit of examples from here because they can ask a variety of different things, not unlike the other ones. Write the standard equation of the circle shown. So this is a different set of kinds of problems. We're not doing tangents and secants and chords and diameters and things like that. We are doing radii. That's going to be part of the circle equation. Here's a standard equation of a circle. X minus h squared plus y minus k squared equals r squared. The h and k are the center of your circle. In this case, the center is at -2, 4. So that's your h, that's your k. Your radius is 4, and that's counted like this. 1, 2, 3, 4. Sometimes they scale by 2s. Be very careful. Or different scalings. But notice that you got to flip the sign that's here. When h is -2, x minus -2 is x plus 2. So x plus 2 squared plus, and then y minus k, k is 4, so y minus 4, quantity squared, equals, and then r squared. This basic nature was Pythagorean theorem. I'm not going to dive too deep into that. You can check 10.7 section if you want to. But this squared plus this squared equals that squared, and that's your r. 4 squared is 16, and that's the equation of your circle simplified. Or in standard form, I should say. Okay, so let's write the standard equations of these ones. That example applies directly to these problems. In order to do these best, I suggest that you pull out the information that you need. And the information I need is the center and the radius, as the example did. So the center of this problem is at 4, -1. And the radius of this one counts 1, 2, 3. So as far as the equation goes, this will be x minus h, quantity squared, plus y minus k, that's y plus 1 in this case, quantity squared equals r squared, 3 squared is 9. They already did one example of it with the raw form, so I'm just going to go straight into that in full. Number 38, we have, careful, this is scaling by 2s. Notice blank 4, or tick 4, tick 8, they go by 2s. And we can read the numbers, that's an 8, this must be a 6. So the center is at 8, 6. The radius, let me put a colon there. The radius, these do count by 2s, so that is 2, 4, 6. And I think that's the only trickery on this problem. This is x minus 8 quantity squared plus y minus 6 quantity squared, and then 6 squared is 36. Last one of that set, number 39. This center is at the origin of the circle, so the center is 0, 0. So there's nothing to subtract from x and y. When we end up writing this part out, the center, we'll just write x squared plus y squared. That's the simplified version of it, equals. What's the radius? This goes by 2s as well, you can tell. So 2 and 4, radius is 4. So r squared is 16. And that's the equation of that circle. Okay, let's move down to 40 through 44. 5 problems there, and then there's a last set where we solve systems. Number 40, let's write the standard equation of the circle with the given center and radius. So with this information, it's these questions I stated at the time, these questions are easier than the ones before because the previous ones we had to pull the information. This one, the information's here. Your h is 0, k is 0. We just saw that as the previous one. That's x squared plus y squared equals, and then 9 squared is 81. I feel like copying down that information though. That's one of my things that I do. So center is 0, 0, and radius equals 9. That's number 40. Number 41, we have a center at negative 5, 2, and a radius of 1.3. So let's go again. This is x minus k, is x plus 5. X minus h, excuse me. Plus y minus k. Quantity squared. We got to do 1.3 squared. It should be 1.69 because 13 squared is 169, and that's just how that would work out. Okay, those are the equations. Number 42 is a little different. They don't give you that information as straight up as you think you'd want to. They do give you h and k, though. So on 42, we have the center as negative 7, 6, if you read on. And there's a point that this crosses through at negative 7, 1. We might need this visual, but we need to find r. We have to find your radius. So we have negative 7, 6 as your center, and a point at negative 7, 1. What's the distance from negative 7, 6 to negative 7, 1? You don't actually need distance formula for that. It's vertically one above the other. They are 5 away from each other. And from center to a point on your circle, that means your radius is 5. So your radius is 5, and your center's at negative 7, 6. That's the information we need to write the equation. So that one maybe took more work, but this is x plus 7 quantity squared plus y minus 6 quantity squared equals r squared is 25. Okay, number 43. The equation of a circle is here. This is not standard form. This is what I believe to be called general form. They haven't called it that, so I'm just covering myself. I believe it's called general form. Where everything's kind of expanded, right? No constants on this side. Nothing is a perfect square trinomial factored down, and that's what we got to do. We got to do that. They said find the center and radius of the circle, then graph the circle. To find the center and radius, you want to get the standard form equation. And then they want us to graph it. So I'll attach graph paper for whatever we do here. Let's first align the x terms together. I want to get these two next to each other. My goal is to complete the square here, build a perfect square trinomial of x minus something squared on the next step. And I'm going to do the same thing with the y's. I got a 1y squared and then plus that 8y. I'd love to complete the square there as well. So then I have something with y plus something to square. I know I'm writing a skipped step. I'm advancing to the next step before I get there. And then we'll get a radius on this side. Now, this equals, and I really ran out of room for myself, but this equals, I subtract 48 over, but whatever I add right here and here, I also got to add to this side of the equation, right? Add something to one side, add it to the other, just like I subtracted 48 to both sides. So, what do we do? Negative 12 divided by 2 is negative 6. That's actually what goes here. Negative 6 squared is 36. That factors to this. 8 divided by 2 is 4. That goes here. 4 squared is 16. And you might wonder, well, why do I have to complete the square if this is the only number I needed? Because it's not the only number you needed. You have to add 36 and 16 to this side of the equation like that. That's part of this part of the equation. I hope that's okay that I kind of ran out of space and room. So negative 48 plus 36 is negative 12, and negative 12 plus 16 is 4. So here's the standard form. It's not the answer, but this is the standard form of your circle, which will reveal your center. Remember, it's x minus h, so h is 6. This is y minus k, so k is negative 4. It flips the sign. And the radius, it's not 4, but, you know, this is r squared. R squared is 4, so r is 2, the square root of 4. Remember, it's always a positive value. So there are those two. They do ask you to now graph this thing, and if I did graph it to begin with, without them asking this information, I would have obtained that information anyway. I would have done all this stuff. I would have done standard form. I would have pulled out these numbers, and I would have graphed, and here we go. 6, negative 4 is the center. It's not technically the circle. The circle is the radius. If you wanted to do this on your own, sketching a graph, you don't have a compass or anything, I would count 2 up from the center, 2 down from the center, 2 right and 2 left, and do your best version of sketching a circle around that. I'm going to use the circle tool for myself and do that, but that's just kind of your idea of what you would or can do. So expand that outward, and then boom, you got a circle kind of like that. So there's the circle, there's the graph, there's the information. Let's go to number 44. Prove or disprove that the point 4, negative 3 lies on the circle centered at the origin and containing the point negative 5, 0. Prove the point lies on the circle centered at the origin. All right, so we know our circle's at the origin. We have some x squared plus y squared equals r squared. And I know this is like these because it's at the origin. Let's figure out what this radius is. The circle that we know contains the point negative 5, 0. If we have a circle at the origin, centered at the origin, the point negative 5, 0, that means its radius is 5. It looks like that. We want to know, and the answer is going to be yes, I already know this. We want to know whether 4, negative 3, boom, is a point on the circle. Now, we're not going to do it that way, but that's what we're trying to figure out. Now, your r, in this case, is 5. So r squared is 25. Here's our equation. Let's substitute. Remember, 4, negative 3 is some xy value. So let's substitute 4 for x, negative 3 for y, and let's see if the left side equals the right side. 4 squared is 16. Negative 3 squared is 9. This is a test to check, and indeed 25 equals 25. So that checks out. So yes, 4, negative 3 is a point on that circle. We made the equation here for that. If it was off the origin, we'd still account for that, and that'd be fine. All right, I got 2 more questions we should finish within the hour. Here's to hoping. Solve the system. Solving a system of equations when you see this y by itself. We're trying to see where these two things intersect. I actually think this one doesn't at all. But we're going to see where these two things intersect, a circle with a line. It might intersect not at all, or once, or twice. Tangent, a secant, or nunesies. So we start with this one here, a system where we have x squared plus y squared equals 25. That is a circle with a radius of 5, centered at the origin. And y equals negative 6, a horizontal line that crosses through negative 6. That's why I don't think it's going to hit. And it's probably not. So what do I do? Substitution. I can substitute negative 6 for y in this top equation. And I get x squared plus negative 6 quantity squared equals 25. And my goal is to solve for x. So this is 36, and I want to subtract the 36 over. The problem is you get a negative value, and we can't take square roots of negatives. This is where you find out you got no real solution. Imaginary solutions? Sure, but that's not on your real xy axis. So no real solution, nothing to solve for. Generally for a solution, by the way, and I'm assuming we're going to have some on this next question, but generally for a solution, we're looking for both the x and the y. That would be the solution or solutions to the system, the ordered pairs where they intersect. So let's see if number 46, we have better fate. X squared, last question, by the way. X squared plus y plus 2 quantity squared equals 1. This is a circle centered at 0, negative 2, and its radius is 1. And then we get y equals 2x minus 3. I think this will hit tangentially. Maybe it hits as a secant, I'm not sure. But what I'm going to do is substitute. Substitute 2x minus 3 in for y, right there. And let's rewrite that equation. Now it'll say x squared plus, and you got a 2x minus 3 there, and then plus that 2 squared equals 1. We'll solve for x with this in mind. The reason we do this is because we get one variable by itself in the equation. Negative 3 plus 2 is negative 1, so I'm just cleaning that up. Now I must expand this here. X squared plus, this expands to 4x squared minus 4x plus 1. I'll let you labor through that if you need to. I can subtract 1 from both sides and they will cancel out. And x squared plus 4x squared is 3x squared. 5x squared. And I have this minus 4x still here. The 1's are gone. This equals 0. I have a common factor of x and x only. And either x equals 0. We'll check the possibility of that. And not the possibility of it. This is where they intersect. This isn't about lengths anymore. These are ordered pairs. Or if 5x minus 4 equals 0, then x will equal 4/5. So there are two different sets of values here, and we are not done. We need to find the points of intersection. What value for y do we get when x is 0, where these two things intersect? We got to substitute 0 for x. We got to substitute 4/5 for x to find that one as well. So let's start with the easy one there. Let's do y equals 2 times 0 minus 3, which is negative 3. So there is an ordered pair where this thing intersects at 0, negative 3. I thought that the center was at 0, negative 1, not 0, negative 2, and with the radius of 1. So that makes sense that it actually hits right there. That's the y-intercept of this graph. And at 0, negative 2 with a radius of 1, it goes down to 0, negative 3. Indeed. And then it intersects at some other part where x is 4/5. Let's do y equals 2 times 4/5 minus 3. And that is 8/5 minus 3. Now 3 can also be written as 15/5. That's getting a common denominator. And therefore that is negative 7/5. I was about to say negative 7/8. So negative 7/5 for that. If you want to write them as decimals, this would, let me first write this, 4/5 comma negative 7/5. But if you want a decimal version of this thing, you could also say or 0.8 comma negative 1.4. That's another version of that thing where they apparently hit. It's basically like you got that circle at centered 0, negative 2 with the radius of that. And this other one's like a line that goes like that. And it's hitting there and there. Those are the two solutions. It's a secant line. If it was tangent, there would just be one solution, but there were two. And guys, that is the last question here. That ought to do it for this one. This is Mr. Robinson. Thank you so much for watching this Chapter 10 review. Next video that should follow in this series is the Chapter 10 test and cumulative assessment. So we'll kind of get those ones thrown in together in one video. But if you need to see anything again, go and check out the description section down below. Check out the IM2 playlist if you want to find more things from Chapter 10. I kept alluding to go to the previous lesson if you want to see things on proofs or if I explain things more with inscribed angles and things like that. But y'all, we finished within the hour. I feel good with that. Take care. I will see you in the next one.